Well, let's review surface area. Very well. Remember that when we had a nice function like y equals to f of x in elementary calculus, to find the length of that function, we just use the integral of the square root of 1 plus the derivative of the function. We take the derivative, we raise it to 2, 1 plus that derivative, and square root of it, then we take the integral where x ranges between a and b. So here you have actually, this is the differential of our thing. So remember that definition. And we move on to our surface area. The differential of our plane. We can use Riemann sum to derive this formula. Now, suppose you have a function. Let z be equal to f of x and y on domain D. And suppose when you graph this function in x, y, z plane, you get a surface. Now, if the partial derivative of f with respect to x and partial derivative of f with respect to y on D are continuous, the surface area is defined as the double integral. The double integral of square root of 1 plus, we take the derivative of the function with respect to x, square it. We take the derivative of the function with respect to y squared and the dA over the domain D. This is our formula. So where does this formula come from? Let's take a look at the graph of this function. For example, you have a surface in x, y, z plane, and this is your surface here. What I'm going to do, I'm going to take one point on my surface, like Tij, and I'm going to take a little piece on the surface on the area, and finally I'm going to add them all together, and by adding them together, I'm talking about the double Riemann sum. Okay. There we go. And here we have just using little pieces here. And suppose we call this guy Tij. This is your Tij. And our goal is to find the area of Tij. What is this area? I'm going to take a look at the projection of this little parallelogram in XY plane. So let's take a look at the projection here. Here we have this. This little guy here. Then here. Finally, this piece here. Oh. And the rest of it, just know that this is just a projection. Let us call this projection in XY plane Rij. There we go. So you have a parallelogram, and your goal is to find the area of this parallelogram. So this side on x-axis is going to be your delta x, and on y-axis, you have your delta y. Delta y. This is just the projection in XY plane. Okay. And you know that to find the area of parallelogram, if we have two vectors, we find the magnitude of the cross product. Well, now this point describes xi, yj, and here this point represented by xi, yj, and here note that your z is equal to 0, so we're not worried about 0. And this point, Tij in the space, represented by xi, yj, and f of xi, yj. So these are the coordinates of our point in the space. Perfect. So everything is set up so far. So we have a tangent plane, if you think about it, and you're taking small portion, small piece, parallelogram of that tangent plane, and our goal is to find the area of these small parallelograms. So now we define two vectors, starting as Pij, vector A, and another vector B. And remember that these are in the space on the surface starting at point Pij. We define A to be the vector. If you look at the projection of A in xy plane, it's going to be the first component is delta x. The second component is projected on x-axis, is going to be 0, and the third component is going to be the partial derivative of f with respect to x at that point, Pij, and times delta x. So this is your vector A. Then we define the vector B as, okay, this is vector B. If you look at the projection of vector B in xy plane, the first component is 0 on the y-axis, the second component is delta y, and the third component is the partial derivative of f with respect to y at Pij times delta y. Now to find this little area, we're going to find the magnitude of the cross product between A and B. This is equal to Ij k. As you can see, we're getting back to elementary calculus. Delta x, 0, f of x, delta x, and 0, delta y, f of y, delta y. Very good. So let's calculate this determinant. Here we have 0 times f of y, delta y, which is 0. Then you have minus f of x, delta y, minus j. Here now multiplying these two, we get f of y, delta x, delta y, plus k in the direction of the axis. Here you have delta x times delta y. So now we need to find the magnitude of this vector. The magnitude of this vector is equal to square root of, write it here, square root of the first component raised to the second power. So you get f of x squared delta x, delta y squared, the second component plus f of y squared, delta x, delta y squared, and the last component raised to the second power, which is delta x, delta y squared. So here you have the square root of, so 1 plus f of x squared plus f of y squared. You're creating that square root of 1 plus f of x squared plus f of y squared. And here, if you factor out delta x, delta y, you're going to have delta x, delta y. As you can see, they're taking these little pieces, and eventually they're going to use the double Riemann sum. And as these areas getting smaller and smaller, that double Riemann sum turns out to be a double integral. Well, let's go over one example. Example says, find the surface area of the following. So what do we have? We have surface area of function z equals to x squared plus 2y and it lies above, so lies above the triangular region. See, in xy plane, with the following vertices. Okay, we have 0 and 0, 0 and 0. We have 1 and 0. We have 1 and 1. Well, let's graph this region. X-axis, y-axis, 0 and 0, 1 and 1, okay, 1 and 0, and 1. So here we have this triangle T. Your x ranges between 0 and 1. There is no problem here. How about your y? Your y starts from 0 and it goes up to this line. What is this line? Y equals to, so this is your T, and this is just your boundary. Very good. To find surface area over T, you get the double integral over T of our function, which we have to take square root. We have to find the partial.
1 plus the partial derivative of f with respect to x squared plus f of y, partial derivative of f with respect to y squared, and dA. So it's over t. So we know that x ranges between 0 to 1, so 0 to 1, and y ranges between 0 to x, 0 to x. Partial derivative of f with respect to x is 2x, so 2x squared, and partial derivative of f with respect to y is just 2. And here we have dy dx. Okay, so this is equal to 0 to 1, 0 to x, square root of 1 plus 4x squared plus 4 dy dx. So your integral can be written as 0 to 1, 0 to x, square root of 5 plus 4x squared dy dx. So this is a function having variable x in it. Let me just erase this. This can be written as the integral 0 to 1. You can write square root of 5 plus 4x squared outside the inner integral 0 to x of dy. Then take the integral with respect to x. This integral, this is the integral of y. Y is ranging between 0 to x, which is x minus 0 or x. So here we have integral 0 to 1, square root of 5 plus 4x squared x dx. You can use u sub in this case. You get the integral 0 to 1, square root of 5 plus 4x squared, 8x dx, and we just multiply the integral by 1 over 8. This is equal to 1 over 8. Here you have the integral of 5 square root of 5 plus 4x squared. Now it is just square root of u du, which can be calculated as 5 plus 4x squared to 3/2 times 2 over 3. Your x ranges between 0 to 1. Let's simplify that. We get 1 over 12. And if I plug in 1 here, we get 9 raised to 3/2 minus, if I plug in 0 here, I get 1 raised to 3/2. sorry, this is 5. Let me fix that for you. Okay. So if I plug in 0 here again, 5 inside parentheses. So here we have 1 over 12. I have 27 minus 5 square root of 5, which can be written as 27 minus 5 square root of 5 divided by